So, hello everybody, we are back to our class again, and we'll be starting in this class finding the solutions of fluid equations in reference to a plasma torch. Plasma torch is a device which are used extensively in the area of plasma processing, in industrial area. So addressing such a practical system and going for the solution in such systems is very much important. In your previous class, what we were doing actually, we are talking about the properties of this plasma, thermodynamic and transport properties both, and we knew that how to calculate them. So we started with the thermodynamic properties, and there we got these number densities and specific heat, physical density, enthalpy. And once you know the number density at a given temperature, then you feed back to that transport property code, and there you find the electrical conductivity, thermal conductivity, viscosity, collision frequency, diffusion coefficients, etc. So that is how actually we started with thermodynamic properties, and then we entered into the transport properties, and that property code will help us in solving the fluid dynamic equations. So with that, we come to the actual problem. If you are really going to solve a practical system, then you need to calculate these properties, and I have just given one example, that viscosity, and these are the coefficients which are coming. Now you see I have written here the upper matrix and the lower matrix. So you see what are the values you are getting over here. It is 10 to the power minus 207. Now it is such a small number that whenever you go to computer and ask him that this is the number I am giving or is the value, it will simply tell you 0, because it is such a small quantity. And when you are going to get a ratio of two such small quantities, then you will see that the computer will tell you that there is an error, 0 divided by 0 error kind of thing. Now, but you understand the point, that is something is 10 to the power minus 207, and another quantity which is say 10 to the power minus 208. If you divide these two very small numbers, you get a factor of 10. Okay, so that is not a small number at all, and which is having some significant value. So, and these are coming in the form of ratios. So although they are small numbers, you cannot avoid this. You cannot assume this as 0, because the ratios are giving some significant values. So that is why you need to have a method to tackle this kind of divisions. You know that although they are small numbers, they are logarithm. If you take, they are not small. So usually you need to do the algebra using in terms of logs, so that you can handle such small number using computer easily. So there are always some way or other to handle this type of things. So you remember that this kind of complexities come when you actually go for calculating these properties, and I am just warning that this kind of things may appear when you go for actually solving the problems, and you need to find out a solution for that. So there are numerous ways to get rid from that and handle with such small numbers, so that you can try out, and one of them is taking log and then proceed for the algebra. Now I come for the equilibrium modeling. In equilibrium modeling, what you are doing, you are solving three momentum equations naturally for x, y and z components. Then only one energy equation. You are not distinguishing the electrons and heavy species, you are assuming the whole as a single fluid, plasma as a single fluid. So in that case, you are solving only one energy equation, and then one pressure correction equation, of course, because that is the key of this fluid dynamics, how to reach the final solution. Then of course one electrical potential equation. This is because you are solving an electrical discharge system. So you must be applying some potential between the cathode and the anode, which will sustain the current and the plasma that is formed within the device. So essentially what we need to solve, three momentum equation, one energy equation and one pressure equation for equilibrium model. But I tell you at this point that when you are going for two temperature model, that time you need to solve two energy equation, one for the electrons and other for the heavy species, instead of only one energy equation. So that will be there, and there will be exchange of energy between the your electrons and the heavy species. So some terms will be positive in the your heavy species equation, and some will be negative in the your electron energy equation, so that one loses and one gains, because they constitute the complete fluid, electrons and the heavy species. So that difference will be there in two temperature modeling. Now here what is there, this is a cathode and this is the anode. From the cathode the electrons are getting emitted, and these electrons are attracted towards the anode, and they form a current path which hits the gas that is flowing through, and that forms the plasma. So I have numbered this like A, B, C, O, C, B, A, like this. So this basically I can say that A, B, C, O, C, B, A, that forms the cathode. Similarly, this yellow zone, they forms the anode. So I have written the upper part as in capitals, and the lower parts as in small letters. So identical places are given the same numbers, like this is capital K, this is small k, this is capital J, this is small j. When you are going for the 2D modeling, then this capital J and small j, they are equivalent. Okay, that capital K and small k are equivalent. So you need not to consider one half of this. Only half of that will be sufficient for 2D simulation. And why 2D simulation is important in such cases? This is because it is having a radial symmetry, a radial symmetry, and if you go for 2D simulation, then computational load becomes minimized, substantial manner. In a substantial manner, the computational load reduces, so you can get the results very quickly. And because of the azimuthal symmetry, because theta symmetry, so you get a solution which is very practical and close to the real one. Although you know that instabilities are always 3D in nature, and you really need to go for the 3D modeling if you want to capture the actual behavior of the instabilities. But apart from that, this is going to give you a very quick and understanding about the device that you are going to handle. So now coming to the fluid dynamic equation, how to solve them actually. So there are, first you need to discretize the differential equation that governs your system. Now I don't know whether you already know about this discretization techniques. There are three major schemes which people use. One is finite difference technique, one is finite volume technique, and one is finite element techniques. I will just give you a flavor of how these techniques go as far as the discretization is concerned. So the first one is finite difference method. The approach is approximate derivatives, replacing them with difference equation using values at discretized grid points. So one term you are now encountering here, there are grid points. So what are these grids? This is because anyway you are discretizing, that is, you are not solving the equation in a continuous fashion. What you are doing, you are calculating the values at discrete points, and if you need some intermediate values, some values at some intermediate points, then you need to go for some interpolation scheme. Okay, there are many standard interpolation schemes available, but you can go for other schemes also, and these schemes are evolving better and better, so you can go for that. So what it does, it approximates derivatives by replacing them with difference equations using values at discrete grid points. So first we need to have a computational domain defined, and that domain has to be discretized at various grid points, and we will calculate the values only at the discrete grid points. Now, what are the features of this? Simplicity. Among all discretization techniques, this may be the simplest one. It is very straightforward to implement on a structured grid. Actually, the problem comes when you have a complex geometry. There, using this becomes tedious because every zone you need to approximate as a structured thing, and then you go for different zones with different structured grids. So that is a bit cumbersome there. But anyway, for simple geometry, structured grid, this is a very useful, and I will say this is a powerful and gives you quite accurate values rather than the advanced techniques. I'll say not rather than, it may be comparable with those advanced techniques. So this finite difference technique is not we should ignore. Now the efficiency, computationally efficient it is, with simple geometry it is very efficient and give you quite accurate values. But the limitation is that it is not flexible for complex and irregular geometries, as I told you, and higher order accuracy is a bit challenging. But if you are happy with a reasonably accurate solution, this is really a powerful technique, and this can be done with considerably less complexity. So I now come to the other one, the finite volume technique. Here the domain is divided into control volumes, and integral form, I have underlined that and highlighted, integral form of the conservation laws, whatever you have got in that fluid equations, so you need to integrate that over the volume. That integral form of conservation laws, that ensures the flux balances across the volume boundaries. So there the whole zone is divided into control volumes, and what you are doing the flux balances across the volume boundaries. Okay, so that balance is giving you this method, finite volume method. The features of that, it inherently conserves mass, momentum, energy. Why? Because you have already made a flux balance across the boundary. So it is inherently inbuilt in this method, conservation of mass, momentum, and energy across each control volume. Flexibility, it handle complex geometry very efficiently, and it can use unstructured meshes as well. Okay, and its robustness is really, many of the commercial codes are using this technique. Now it is well suited for problems with discontinuities such as shock waves as well. Okay, so this is a very powerful technique, finite volume method, in which the conservations are inbuilt. Conservation of mass, momentum, energy are inbuilt in such a system because of the particular nature of integral form of conservation laws, that is which balances the fluxes across the volume boundaries, and it can handle complex problems, complex geometries, unstructured meshes, and systems with discontinuities as well. Okay, so this is the second one. Then there is a third one, which is called finite element method. The approach is, it divides the domain into elements and uses variational method to minimize the error in approximating the partial differential equation solution. Now the features of that, it excels in handling complex geometries and boundary conditions. It is wonderful in that way, and this is mostly used in the stress calculations, your thermal management. These are very frequently being used, and it allows higher order approximation, adaptive mesh refinement. So when your adaptive mesh refinement is necessary during the simulation, this is one of the most useful one. And the complexity is that it is mathematically intensive and computationally demanding. So when you have enough resources, computational resources, and that coding is not a problem, then you can go for this. And there are a number of commercial softwares which are using APM method for doing the studies of say thermal management, or stress calculations and all these things. So these are very standard techniques. So I have now told you that we can use finite difference method, finite volume method or finite element method for solving the fluid dynamic equations. So when you are saying that we have two codes, one is fluid dynamic code, one is your properties code. I told you before that how to manage the properties code. What are the challenges, how the difficulties come, and what the exact look of the equations. Now for fluid dynamic equation, again there are things that you need to use some technique to solve those equation numerically. So what you do first, you first choose the computational domain, then you discretize the domain either in volumes or elements, then what you do, you either you use finite difference method or finite volume method or finite element method to solve those equations, discretized equations. Now finite difference method is simple, but it is not very useful for complex geometries, whereas in finite volume approach, it is very ideally suitable for plasma like fluids, where you need to maintain the conservation equations at every zone. So this method, finite volume method, this is inbuilt, and finite element method is it is a bit computationally intensive and mathematically intensive as well. So most of the studies what I will be showing now, it is based on finite volume methods. So just to give you an idea about how we are doing that thing, I have shown you already the geometry of a plasma torch. So this is the cathode. As I told you that I am keeping this capital and the lower part is small, they are identical, B are identical, A and A are identical. Only if you are going for 2D simulation, only considering the upper part, that capital letter part is sufficient, and most of the studies that I will be showing here are 2D simulations. So since 1/2 is sufficient for presenting the parameters like temperature, velocity, thermal conductivity, electrical conductivity, or species distribution, current density, pressure. So only 1/2 is sufficient to present them. Then there remains the other half. So what I will be doing in most of the presentation, I will be using the other half to present the other fluid, parameters of the other fluid. When I am going for two fluid model like non-equilibrium model, I will be using the upper one, say for electron temperature, then lower one I will be using for heavy species temperature. This is because geometry wise they are identical. Okay. So if I am showing something over here, then corresponding value for say heavy species temperature will be at the point here. So they correspond to the same point because I am using a 2D model because of availability of space, because spaces are available here. So I am using the space for comparing these two values, electron temperature here and corresponding heavy species temperature over here, so that you can make a direct comparison. So now coming to the boundary conditions, these are the boundaries. So what are numbered here? So at each boundary we need to apply some boundary conditions. Okay, like you see here I have put one GA, the first one. So GA is over here. So this is a channel surrounding the cathode, which is through which the gases enter. Okay. So here the entry point, the pressure is 4.74 atmosphere. I have kept this because this is entering from the cylinder and its pressure is that high. Or if we are using a compressor to inject say air, that compressor is delivering the air at such a high pressure, 4.74 atmosphere. Similarly, for U, V and W, use the axial velocity, V is the radial velocity, and W is your tangential velocity, that rotational velocity. So what we are doing here, when I am giving a W value and when I am giving U, what I am doing, I am injecting the gas, giving a swirl motion. Okay. So that is why I have put over here, and the T, because here at this location G, A, this is entry point of the gas, say air it is entering here. So at that location, The gas is entering at room temperature only. There is no plasma over there. So that is why the temperature is 300 degree Kelvin, that is 27 degrees centigrade. So, and there is a potential equation. So for that I have put del phi by del x is 0, that is along the axis actually there is no variation in potential over here. So that is quite expected. Similarly, for other places like A, B, C, this is the zone. There I have put U equal to 0, V is equal to 0, W equal to 0. So that is something called no slip condition. That is, whatever the layer of the fluid that is in contact with that, that is not moving here. That is attached and they are staying fixed like that. Now, similarly for other places also we need to give the boundary conditions accordingly. So I am in this slide I am just want to tell you that how to put the boundary conditions at the boundaries. Okay. Now you know that once you give the boundary conditions at every location that is required, then we can proceed for the simulation, because you are solving this boundary value problem. Those equations, whatever partial differential equations you obtained, you have discretized them, and in the discretized domain, one end lives at one boundary, the other end lives at the other boundary. So at the boundary, what will be the values that you are specifying over here, and it is very much important to specify boundaries at all the points. Now you see here there is something here that is where is n, there is something del u by del r is 0. So what is the u? U is the axial velocity. So u is the axial velocity. So del u by del r is 0 means there is no variation of the your this thing velocity, axial velocity along the radius at the axis. So there flat at the axis, exactly at the axis, there is no variation in u along the radial direction. So whenever you are considering say Gaussian shape of profile, you will see that del u by del r at r equal to 0 is 0. Okay. So this n o you are seeing over here. So you see here n and you see here o. So along this boundary, what we are putting, that this condition is there, that axial velocity has no radial variation exactly at the axis. Similarly, we are considering the same for temperature as well. So this is just an example how to apply the boundary conditions. Now you see here that ABC here, ABC, so this is the cathode surface, and what cathode we are using? Usually tungsten, and typically we heat it at a temperature say 3000 degree Kelvin, so that you can serve as a good electron emitter, thermionic emitter. So you know that melting point of tungsten is around 3500 degree Kelvin. So it is well below that. So that there at that high temperature it can emit very efficiently. So this is the zone where we are applying the boundary condition as 3000. So this way actually we need to apply different boundary conditions for different parameters, looking at the exact system what we are studying and what may be the possible values. Now you know that here where it is emitting, there is a rectangular box around the capital O. This box usually represents the hafnium insert for thermochemical cathodes. So a small pin of hafnium is inserted here, which actually emits the electrons. So this zone, this O and the adjacent one, that is Q, OQ, you need to define the profile of the current density. How do you know that profile? So you have to do some experiments at that particular temperature. What is the current density distribution? Or when you are passing a current, you know that you have to do the current conservation equation. So if you integrate current over this area, that will give you the total current. So whatever profile you are choosing, the parameters should satisfy the total current. So that way you can define a current density over this cathode zone. Okay. So that again will be a boundary condition when you are going to solve this kind of system. Now here I am just showing that current density distribution, how you define in this zone, this O and this is Q. In this OQ zone, actually this is Q and this is the center part is O. So in this OQ zone, how you define the temperature? So this is the experimental results of temperature, and what we have shown that you know that the current density is like this, and then what we are doing, we are integrating that and trying to get the total current, and that should match with the current that you are passing. So total current here is 200 ampere. So we have used a profile which ends at say around 0.5, where your radius is 1 millimeter. Halfway it is ending over there. So at r equal to your capital R by 2, the diameter, half of the diameter, the profile ends. So this is the current density profile, which has been in conformity with the experimental data, and we have only taken the shape. We have chosen the parameters of this profile matching the total current. So that way you decide what will be the current density over the cathode surface. Once you do that, and this is the grid generation. This grid generation is very simple. It's a finite volume grid, and you can see that the grids are not uniform. We have used a non-uniform grid. There are zones where the things are varying very rapidly. At those zones, we need to place the grid points very close to each other. Whereas where the parameters are not varying significantly, we can keep a coarse grid like this one. Okay. But here the things are changing rapidly, so we need to capture those physics. So we need to keep a denser grid over this zone. Now here actually there are many techniques, but you can generate your own technique to generate the grid. And when you are starting a very particular system and you are generating your own mesh generation, this is called mesh as well, mesh generation technique, then sometimes it is beneficial because you have customized it to your particular device. And if you want to change some parameter, just change that value and the grid gets generated automatically. So just one click you can change the mesh. So that is the kind of thing. Now here I am showing you that for the kind of torch that you have seen here, for which the mesh I have shown, I have divided the whole zone into 23 points definition, and these 23 parameters are like this. Here 1, 2, 3, 14 and then 23, and they are marked over here. Something is like this distance, something is like this distance, and something are horizontal also. Your vertical, something are horizontal. And if I define these lengths, then the geometry is automatically defined. Now suppose I want to increase this bore diameter, then what is here? There is something called W1 is there and something called W10 is there. If I change these two parameters, sometimes it will be cylindrical, sometimes it will be divergent, sometimes it will be convergent. So this part we call nozzle. So if we want to study convergent nozzle of different types of convergence, or a simple cylindrical channel, or a divergent nozzle, I don't need to do anything. Just I change this parameter W0, W10 and W11 and the job is done. So that is so simple when you customize your grid generation method. So this much I tell here, and you come to know about that how the mesh generation is important, how to discretize, what are the different techniques to solve them, and how to make customized grid generation technique to get a solution very quickly for a particular device that you are handling. So I will give you back in the next class to show you the actual simulation results. Okay, thank you.